welcome everybody to our webinar today. Today we are going to be speaking about, let's see here, implementation topologies for distributed SQL. Thanks for everybody for joining. Again, I know we had a shout out from a team down in Atlanta. Hi everybody there. We are in New York City. I am joined by my friend Jesse Seldes from our education team. Let's put our faces on there for a second, all right? Come on over.
Everybody.
Hi everybody. Hey. All right, they don't need to see us. A bit of housekeeping before we get started. Please do ask questions throughout the webinar. I'll be monitoring those in the QA panel, and I'll pass them on to Jesse, or be able to actually answer them for you. At the end of the webinar, we will conduct a survey. My friend Maria will put that into the chat at the end of the webinar, and so you'll be able to do that. We are always endeavoring to get better, so your feedback is awesome. And then, before anybody asks, yes, definitely a recording of this will be available to everybody after the event. As part of our follow-up, we'll send a recording out to everybody. So, again, thank you for joining us. Again, I am Jim Walker. I'm product marketing here at Cockroach Labs. And again, Jesse.
Yep. Hi, everybody. Jesse Seldes. I lead the education team here.
Cool. And so what we're going to talk about is implementation topologies for distributed SQL. Now, I'm going to give you about 5 to 10 minutes just to lay down a little bit of distributed SQL stuff, but more importantly, some of the key characteristics of a distributed SQL database that need to be considered when you're actually deploying one of these tools or one of these databases. It is unique. It is different than kind of a traditional approach to, download a binary, start it up, and just start, accessing the database, right? I mean, and it's not just sharding. We're doing some really interesting things, and when you become distributed and global, there's some really, when you start to overlay the logical with the physical world, there's some interesting concepts that have to come out. But let's just talk about distributed SQL first. I mean, ultimately, this is an evolution of the database to ultimately be kind of a cloud native distributed system, right? And so, there's emergence of distributed systems, and we need a database to actually coincide with that. And that's really where distributed SQL came from. Now, this is SQL, so it's going to speak SQL, number one. It isn't going to add, it adds complexity because, you have to think about these things that Jesse and I are about to talk about, but it should basically ease the complexity of scaling out across the entire world. And it should be always on and should be resilient. That's the whole point of being a distributed system is to be resilient. We're going to show you a lot of that. And since it's a database, well, it needs to be ACID compliant. Here at Cockroach Labs, we're really proud that we actually can provide serializable isolation for that I in ACID. And so that's like a key characteristic. But it actually comes into play as we're talking about these deployment topologies, because as transactions are happening in different parts of the planet, where is that data? What is the latency to get to that data? And we'll talk a lot about that today. And then finally, if you're going to be a distributed SQL database, ultimately, you're going to have to tie data to the location. There's lots of reasons. We're going to, again, all of these things actually will be touched on because I think that all are affected by the way that you deploy the database itself, where the data lives, where each row in a table lives actually becomes extremely important. And you kind of got to think about that as you go global and scale out a distributed SQL database. So at CockroachDB, or at Cockroach Labs, CockroachDB, basically we have nodes within a cluster, and each node of our database is a complete database in itself. You could basically spin up a single node and write against it if you wanted. You could do 3 nodes in a single region. You could do that. We're going to show that. But in CockroachDB, we provide all the capabilities around integration and management, security. We actually have a cost-based optimizer. We're doing some vectorized query execution. There's some really interesting things of CockroachDB in its own entity itself. But the smallest atomic unit of CockroachDB is the single binary it is, and each instance is a single consistent gateway to the entirety of the database. And the entirety of the database is really represented as a cluster. It's a cluster of nodes. And the way that we can scale out CockroachDB is if we have a cluster, say we have 3 or 4 nodes running, I could take that binary, I could spin up a node right here on this laptop, I point it at the cluster, it has a TLS connection, and voila, it's participating in this database, this clustered distributed database. And so we're able to take this small atomic unit and attach as many as we want to this cluster, and boom, we have some really cool things going on. Via global coordination, it's going to basically gain consensus across all these transactions. So when one transaction occurs on a record in, say, New York, and the same record is being accessed in, say, Spain, and they both want to write to that row, who wins, right? Like, and so, so Cockroach is going to actually deal with that. And however, there's latencies. And again, we're going to talk about deployment topologies and how that affects, right? Again, if you just point a node at the cluster, it's going to rebalance all the data too. So the cluster actually rebalances and deals with all this data. And you're going to actually see this in motion as Jesse gets into, I think, the third topology pattern, or the second. I'm not sure. We'll see it. I trust you. You'll see it today. We can kill nodes, and you'll see that the data that was in those nodes actually just rebalances across the remaining rows, the remaining nodes, right? And this is kind of that resilient nature of a distributed SQL database and what we've done here at CockroachDB. And then finally, tying data to a location. Lots of people think about this from a compliancy point of view, and it's important for compliancy. Of course, we don't want data to just live anywhere. There's this increasingly complex web of privacy regulation that's happening across the planet. And so how are we able to address those things? More importantly, if you're doing distributed SQL, where data lives becomes incredibly important, because ultimately, we're fighting against the speed of light here. And so that's exactly what we're going to talk about today, right? And when you deploy these things, my own segue into my own slide, Jesse, I can't believe it, right? In a geo-distributed environment, I can't get better than the speed of light between, say, what is this, New York and Spain, say it's 100, 150 milliseconds, whatever that is, right? Here, what we do is we try to optimize for that, right? How can we actually, shrink the time of these transactions? There's lots of things we've done in say a single region instance that actually speed the database, but we focus a lot here on how we can enable you to have a database that's actually going to span multiple regions. And we're talking global regions. What can we do in the database to configure how data is stored and where it's stored and how you're accessing that data via, which nodes are performing operations on this and whatnot. We do a lot in the database itself, and we're going to show off some of those features today to actually shrink the latencies across these broadly dispersed geographies. And so I think that's the number one thing you have to think about when you're deploying a database, a distributed database, in multiple different regions, is those latencies. The second is resilience. What do you want to fail? What's your appetite for failure? Is it a single AZ? Is it a region? Is it a disk? There's lots of different ways in which we can actually distribute the data within the cluster, so that when, I guess that's, oh my gosh, my friends down in Atlanta, that looks like their cluster's on fire. When that cluster goes off, and that region goes out, how do you survive a regional failure? We're going to show you a topology pattern of how you can actually survive a regional failure of a database. Of a couple of nodes of a distributed database, right? And that's really the secret to what Cockroach is doing. And then finally, again, I spoke a little bit about compliance and how do we actually tie data to a location. And so we can do all those different things in CockroachDB, and we just want to walk through why topology patterns and how you deploy actually kind of play to these things. However, before I get into this, there's a couple of concepts that Jesse is going to use during the demo that I think are pretty important to understand from the core architecture of the database itself, so that the demo will actually make a whole lot more sense if we just explain three things. I'm sorry, I'm the marketing guy. I got a lot of slides, but I'm going to try to get over to the bits and bytes. Jesse's going to do some command line. It's going to be exciting. But there are three kind of core technical concepts that are really critical to understand. Number one, the concept of a range. Every table in CockroachDB is basically represented as a monolithic ordered set of data, right? And so here we have a dogs table. You see it's all ordered by alphabetically by dog name. There's Carl, there's Downey, which is one of my favorite dogs on here. That's Maria's dog. Lula, Muddy, Petey. And these are all really important dogs to us here, but you'll see this is an ordered table. What we do is we take every table and we break it down in this contiguous 64 megabit ranges. And each range is used and manipulated in the concept of this distributed database. When we write data to a range, and that range is going to pair 3 times, and I'll explain that on the next page. But because these things are in order, it allows us to do some really cool things, like some really efficient range scans and some other things. But the concept of a range is what I want to get into first, and that is basically a piece of a table, but an ordered piece of a table, which is actually really key thing. And every table is broken down into ranges, and that is what is distributed. Now, when we distribute, we use this thing called RAF, which is a distributed consensus protocol. So for each range, what we're doing, we take that range, for instance, like let's say the Lady, Lula, Muddy, Petey range there, right? That segment of that table. And we're actually going to write that in triplicate into the physical nodes of the cluster. And we're doing that so we can survive a failure. So if one of these nodes went down, we still had 2 copies of that data, right? That's one of the ways in which we distribute data. Our architecture webinar actually went through all the ways in which we do that, but I don't want to get too deep into that. But that's called a replica group. And so that replica group is the 3 copies of the blue range here, which is Lula, Lady, Lula, Muddy, and Petey, right? And so that data gets written in triplicate. So we're using RAF to do that. Now, there's one last concept in RAF that's actually really important, right? Ranges, distributed consensus, or how we distribute the data. And then the last is this thing called a leaseholder. And for each RAF group, this is the blue group again. For each RAF group, they basically nominate one of the replicas to be the leader. And the leader basically is what controls all the transactions for that group. That's really how we're able to get consensus, right? We're going to be able to ensure that all of the data in that group is correct across the 3 physical places where it lives, because it's all actually going through that leaseholder. And so this is a really, really important concept, because if a transaction is occurring, right, it needs to go through a particular leaseholder. I wanted to write a data, a new record between, I don't know, Lula and Muddy, who is, I don't know, Maddie, let's just say. I need to find the leaseholder to do that. And if that leaseholder is in Europe, I've got to go all the way to Europe to do that. And so this leaseholder concept is really, really critical to understand, because we can actually control where these things live. And that's going to have an incredible effect on latencies. And Jesse's going to show you some really interesting ways of actually controlling that in our database using zone configurations. I don't know, I'm just a marketing guy. There's some great technical stuff that Jesse's going to talk through. But these are the key 3 concepts I think are necessary to understand kind of things that we're going to talk about, right? Range, just how we distribute, and then the leaseholder itself. So with that, I'm going to stop the slides, and well, Jesse, you have a few slides, don't you?
I do.
You do. So
I do.
I'm going to hand it over to Jesse so that he can actually show you guys how this all works then.
Awesome. All right. So hello, everybody. Once again, I'm Jesse. I head up the education team here. And I'm going to actually show you how a lot of this stuff works by demonstrating some real live clusters. We have 4 clusters I'm gonna walk you through. But first, I'm gonna talk about the fictional application that we're using throughout these clusters, across all of these clusters. Mover is an open source application that we built. It's a peer-to-peer vehicle sharing app. And I just want to go over the basic behavior, the basic workflow of the application real quick. So a user loads up Mover and sees 25 of the closest vehicles. The user signs up for the service, maybe adds a vehicle to share with others, but more commonly reserves a vehicle and starts a ride, and sometimes applies a promo code when that's available. So a marketer at Mover is applying promo codes that might be used by users. And then during a ride, Mover is tracking the location of that vehicle for possible machine learning purposes or for calculating the fare, that kind of thing. And then, of course, the ride ends and the vehicle is released. So it's a fairly simple workflow. And this is the schema. I'm not going to go too deep into this, but I just want to share it with you, and it should actually resonate with what I just said. So there's a users table, a vehicles table, a rides table, a vehicle location histories table. That's the table that's recording those location pings during a ride. There's a promo codes table and a user promo codes table. One thing I want to point out here is the promo codes table is unique compared to the others. The promo codes table is something that we call a reference table or a lookup table. The values in that table don't change very often, but they're read a lot. You look up the values in them a lot, but they don't change very often. You know, a marketer is going to maybe add one every who knows how often, once a month or something like that. But it's a table that's read from a lot. So this is quite important. It's going to play into one of the topology patterns that we use to make most efficient use of a table like this. The rest of the tables, the thing I want to point out is you'll notice that each of those other tables, users, vehicles, rides, and so on, they have a compound primary key where there are 2 columns in the primary key, starting with city and ID. I want to call this out because in these cases, tables like this, the rows in the table can be they can basically be linked to a geographic location. In this case, it's going to be city. And this is important when it comes into play in some of our more important topology patterns for multi-region clusters, where we geo-partition data, because we can actually use that sort of geo column to break up the data and sort of physically align it with users. And we'll see that in action.
So Jesse, this is one of those places where distributed SQL is very different, right? You've got to think about the tables and the data that's in them, because that's going to actually affect the topology and how things are going to perform in the end, right? Absolutely, absolutely, yeah. Because your cluster might be very broadly geo-distributed. If you don't think about the schema design a little bit up front, you're not going to gain the control of the physical location of the data that you're going to need. Right. So, for instance, so Mover, it works in, well, I guess our example is going to be one city and then two cities, and so the city actually becomes really important because you want that data to actually reside there. Yeah. That's going to be stored in that table. The table is actually going to drive, those rows are going to be in a particular location, right? That's right. Yeah. And then reference data, it just needs to be fast everywhere. Actually, reference data, you just need to be able to read it really quickly. Yeah. I just think this is one of those unique things that is very different than the traditional world. You had to actually think about this stuff. Yeah. And this is the stuff that we work with our customer partners on deploying all the time, right? Yeah. Absolutely. Cool. Absolutely. So with that, the basic story that we're going to move through is that Mover, it starts, local. Somebody's developing it in New York City, and then it goes live just in the East Coast, let's say just in New York City. And so we're going to start with what we call our basic production topology pattern. That's just a single region pattern. But the story goes that Mover does very, very well and then expands to cover the entire United States. So that means that it expands into the Midwest, expands into the West Coast. And so the cluster grows and scales, and the techniques that you use to get the right latency and the right resiliency that Jim mentioned are very important. So this is the basic story, and now we're going to actually walk through and look at how we achieve this. But again, just to reiterate, latency and resiliency are very important. In latency, when data is distributed, when there's replicas that are located in different places, and your requests are always having to be routed to that special replica, the leaseholder. You can't get around the speed of light. You have to travel between locations. So latency is really key in a distributed database, and we have to try to minimize that as much as we can. Resiliency, because the data is distributed and it lives in multiple places, and we use Raft consensus protocol, we get resiliency because we have multiple copies. But you still have to think about the location of those copies to get the right level of resiliency. And we're going to look at different I always think we're basically fighting two laws of nature, right? The speed of light and everything fails. Absolutely. And that's what you got to think about. Yeah. Okay. So with that, all right, finally, fingers on a keyboard. Yeah, let's dive in. And we're going to start with the first cluster is actually a very simple cluster. It's in a single region with 3 nodes. Let's look at this nice node map view here. We can see that the cluster is only deployed in the US East region of the United States. There's 3 nodes in there. If we drill in, you can see that each node within the US East region is running in a different availability zone. And this is what we call the basic production topology pattern. You can find lots of information about it in the docs. But I do want to call out something else that's happening here. There's a separate VM also within the US East region. That's where Mover is running. And on that VM, we also have a load balancer running. We're using HA proxy. So all of the Mover requests are going through the HA proxy load balancer, and HA proxy is making sure that the requests are being balanced across the nodes. And real quick, you can see this very nicely if you just filter by node. So we can see there's a whole bunch of SQL happening on node 1, node 2, node 3. So it is being balanced. There's another way. If you look at the SQL dashboard, you can see the actual connections. There's 100 connections across the cluster, 33 on the first node, 34 on the second, and so on. So it is, the load is being distributed, and this is very important. Actually, you want to always load balance. The thing to really look at here is the P99 latency. That means 99% of all queries are
2.6 milliseconds. So this is in a single region. It's just very fast. And one of the key reasons it's so fast, if we look at this debug page called network latency, Jim mentioned speed of light. You have to move between physical nodes and physical regions. In this case, all the nodes are in a single region. And so you can see in this view that it's sub-millisecond. It takes less than a millisecond, a half a millisecond to get from any node to any other node. So it's very, very fast. If we look at this view, this is showing how data is distributed. So let's just take this promo codes table. Jim explained that a table generally maps to one or more ranges. In this case, all the data in the table is just in one range, but you can see that the range has 3 replicas, and one replica is in this availability zone, this availability. They're spread across the 3 availability zones. And so what that means is, when requests are coming in, they have to be routed to the replica that's the leaseholder, and then it just goes back to the gateway into the client. With writes, there's more routing, more of the replicas are involved because we have to achieve consensus. But the key here is in a single region, network latency is so low that it's inconsequential and you still get incredibly fast performance. So without doing anything at all in a single region cluster, you just get good performance. 3 nodes, very, very good performance. I also, the fact that we're distributed across 3 availability zones in this one region, and the fact that the data is balanced across those availability zones. So for every range, 1 replica is in each of the AZs. What this means is we can lose an entire AZ in that region and still retain a majority of all of the data in the cluster. And so I'm actually going to demo that for you. So here we're on the client VM in the US East region of this cluster. Let me grab a command real quick. And so we're on this VM, and I'm using an internal tool that's just sending a command to tell the node in one of the availability zones to just stop. I'm just going to do that as a way to kind of simulate an AZ outage. Oh wait, I don't want to be on that node. I'm sorry, I want to be on my local machine.
Of course, it's a demo, Jesse.
Yeah.
Something has to go wrong.
Yeah. So let's go back to the screen, and we can see, hold on a second.
There we go. Okay.
We can see here, we're on the cluster overview screen, that node 3 is shown as suspect. We're calling it suspect. CockroachDB hasn't heard from it, and so immediately thinks, oh, this is suspect. Something's going on here. It's not considering it dead yet. That by default, it takes 5 minutes for CockroachDB to consider a node dead. At that point, it would rebalance all the replicas on this dead node to another available node. In this cluster, there wouldn't actually be another node that it would rebalance to because it never puts more than 1 replica on a node. But the key here is that we've taken 1 node down. Essentially, this means we've killed an entire AZ, and the application continues making progress. So because it can always achieve consensus, because 2 or 3 replicas are always available for whatever a mover's trying to do, it just keeps going uninterrupted. You can see the latency is 2.8 milliseconds. It's not very effective. So this demonstrates that an AZ level resiliency within a single region. Okay, but that's, and you don't really need to do very much in a single region. So let's going with that story that mover is doing really well, and it's expanding, across the entire United States. So now we're in a cluster where there are 9 nodes now. Let's look at the map again. And now we still have those 3 nodes in the US East region, but now we have 3 in US Central and 3 in US West. And the other difference is that there's an instance of mover running in each of these regions. So in the US East, mover is running, passing requests through a regional load balancer that's redirecting to those nodes. There's mover in Central running through another instance of HA proxy, rebalancing to the central nodes, and the same thing in the West. And so it's deployed like that, but we haven't actually done anything else. And I'm doing this on purpose to show you the effect of latency when you're deployed across multiple regions. So you can see that the P99 latency has gone up, significantly. It's 104 milliseconds now. And again, let's go to the network latency page, and we can see what's behind this. So now we can see that when a request has to travel from node 1 over in the US East region over to node 9 in the US West region, just to get over there, it's 66 milliseconds, and then to get back, it's another 66 milliseconds. So all of those operations, so if it's a read and it's coming in the US East and the leaseholder for the data is on the West Coast, it's going to take 66 milliseconds to get there, retrieve the data, and come back. So it's going to be slow. For writes, of course, because you have more replicas involved, there's more network hops involved, it's just going to increase the latency. And this is just sort of calling out that, when you don't do anything, you're not going to get the absolute best performance that you want. And I also want to show you the data distribution page, if it loads up here. Just one second. In the previous cluster, it was in a single region. You saw for a range, there was one replica in each AZ. Now you'll notice, let's look at the promo codes table again, that instead of having one in across 3 AZs in a region, now you have one replica in each region. So CockroachDB just very intelligently understands the locality of the cluster. The nodes were started with this locality information. It says, I'm going to try to diversify the location of replicas across the highest level of locality. And because of this, you really do have to deal with network latency. So again, this is a cluster where we're deployed across multiple regions, but we didn't do very much of anything, and the latency went up significantly to, what is it at? P99 is 104. So now we're going to go to another cluster. It's the same exact setup. It's still 9 nodes. Everything, movers running the same, HA proxy, everything is the same, but you're going to notice P99 latency is now down to 39.8 milliseconds. So how did we do that? Well, we did that by applying two of our multi-region topology patterns. Let me dig into the actual table schema to show you what I'm talking about. Let this load up. So when you looked at the schema earlier, you might remember that promo codes is a little special. Rides, all the other tables, they have a schema that allows us to have some knowledge of geography, so city. So I mentioned that in these tables, the primary key is compound city ID. City is actually the first key. So this is the table right here, but what you're going to notice here is that we have actually partitioned this table. So instead of the table being sort of known as one thing, it has been broken up into separate partitions. So we have a New York partition, we have a Chicago partition, and we have a Seattle partition. And at the key value layer, this has broken up the table into separate ranges per partition. And so we defined these partitions, and then we defined some zone configs. And this is really crucial. So on a table like this, the tables where we could partition by city, we then applied a zone config and said the Chicago partition of the users table, we want to make sure, absolutely sure, that there's one replica in the US Central region. That is where Chicago is. And then we applied what we call a lease preference. And we said the leaseholder for that partition needs to also be in the US Central region. And what this is all about is it's saying traffic from mover in the Midwest is always going to find a local leaseholder. The leaseholder for the Chicago partition is always local. And so those read requests never have to leave the region and therefore are very, very fast. And we did the same thing with New York, and we did the same thing with Seattle. However, and we'll look at this in a second, we're only constraining the leaseholder of those replicas to the central region. Otherwise, the other replicas are still balanced across the other regions. So writes do incur cross-region latencies, but the benefit you get, we'll show you in a second, is you're able to survive an entire regional failure. So those are the tables that you can geo-partition. I also want to look at the promo codes table. I mentioned that this table is not one that where the data inside the table can be tied to geography. So this, and it's a reference table, a lookup table. It's not changed very often, but when users start rides, they're referencing it all the time. And so for this table, we've used a different pattern that we call the duplicate indexes pattern. And what we've done here is we've created two additional indexes. So the main table, we just call it the primary index. We've created two additional secondary indexes. Each of them is basically an exact replica of the primary index. So we've created one secondary index that we're calling index east, and you can see it's storing all of the columns in the table. And we've created another index, index west, again, storing all the columns in the table. So there are three complete copies of this table in essence. And then again, we've used zone configs, and here's what we've done. We've said for the primary index of this table, you know, we want to make sure there's one replica in each region, but we want the leaseholder for this index to always stay in the central region. And for the east index, we've done the same thing. We said the leaseholder needs to be in the east in the US East region, and for west, same thing here. And there's some really cool magic happening here that I want to show you. So basically, what happens when a request comes in, let's say in the West Coast, it comes in to read from the promo codes table. Our cost-based optimizer is aware of locality, and it's aware of the fact that there is an index that can meet the requirements of this query in the region. There's a leaseholder, so it uses it. It doesn't go to the leaseholder for the whole table. It says, oh, there's an index here, the leaseholder's here, we're going to use it. And so again, reads in every region are completely local as a result of this. Writes still have to go across regions. And I'm going to look at this real quick. I'm going to go to the statements page. I'm going to filter by app here. So the mover running in the West Coast. And we're going to go look at this select from promos query. And we can see right here that it is using that index in the West Coast. So just to sort of, you know, prove the point here.
So it automatically did that for us. Automatically. The covers, right? So the CBO, the cost-based optimizer went and automatically optimized for that.
It absolutely did. All you had to do was, as I showed you, create a few secondary indexes and sort of pin the leaseholder to the regions, and the cost-based optimizer handles everything else.
And the pinning of that, Jesse, that's all done through zone configurations, right? And so the zone configurations, is that done when you create the table, or is that after the fact?
That is after the fact. So you create the table, and then you can create zone configs, and you can change them without needing to change the schema. Without making any changes to your application, zone configurations can be managed completely independent of that.
That's cool.
Yeah, yeah. Okay, so let's see here. All right. So I think what I want to do now is demonstrate, as I mentioned. Actually, hold on one second. I want to actually prove to you where the replicas are. So we're going to go here. We're on the VM in this cluster. And I'm going to run a query and then explain it to you in just a second. All right, so I opened the SQL shell. I have the cockroach binary on this VM, and I just pointed it at actually the HA proxy load balancer, and it opened a SQL shell for me. And so what I'm going to do now is I'm going to use this show ranges command to look at where the replicas are for this vehicles table. I have to make this little smaller so you can see what's going on here.
Before you do that, Jesse, I want to point out one thing.
Yeah.
What you just said was actually kind of interesting, right? So you pointed the SQL shell at the HA proxy, and it went to basically.
Yeah, one of the nodes.
One of the nodes, doesn't matter, right? Because every node is a gateway to the entirety of the database, and any node could actually take a transaction or do anything we want to do, right?
Yeah, absolutely, absolutely.
Yeah, cool.
And so we're looking at the vehicles table here. I'm going to make it just a teeny bit smaller. But basically what we see here is there's a bunch of ranges for the vehicles table. And so there's two ranges for the New York partition, 2 for Chicago, 2 for Seattle. And we can see here that for this range of the New York partition, one replica is on node 3 in the US East, one is on node 6 in Central, one is on node 8 in the West Coast. But the leaseholder is on node 3, which is in the US East. And that was the geopartition leaseholder. The zone config that we defined on this partition constrains it to the US East. And in 19.2, we're also going to list out, right now it's just listing the localities of the leaseholder, but we'll probably list out the localities of every node so you can sort of verify that zone constraints are actually working here. I'm going to show you one more command here. We're going to look at the promos table because we had a different topology pattern applied to that table. So we're looking at the ranges for the primary index and for those two secondary indexes, right? So for each of them, there's 3 replicas, and those replicas are spread across the regions 369, 148, 1 replica in each region. But in this one, this is the primary index, and we said the leaseholder should be in the central region, and it is. It's on node 6. This one is for US East, and the leaseholder is on node 1 in US East, and this one's on node 7 in US West. So this is just proving what I was telling you before. You saw it in the statements page that the cost-based optimizer is going to detect this, and it's going to always use that local replica to serve reads on this table. All right. So next, I actually want to show you a region-wide failure. Because all data is distributed across the 3 regions. Let me get out of here. What we're going to do now is we're going to take down the entire West region. So I'm taking down the 3 nodes in that region to simulate an entire region outage. And you're going to see that because the cluster can always achieve consensus. All right, so you can see here that those 3 nodes, they're all in the US West region, just went down. The cluster thinks they're suspect. They're not available. However, the cluster continues. There's a little dip in throughput, but then it's going to go back. It's going to go back up. The P99 latency is still at 35.7 milliseconds because the data is distributed across the 3 regions, and you still have a majority of all the ranges. Mover just continues uninterrupted, and so this is incredible resiliency, across the entire United States.
What was the latency on this before we actually bought the 3?
It was similar.
It was very similar, right? Yeah. And so you're basically still getting the same latency, and you're resilient, and that's just amazing, Jesse. Sorry, but that's kind of cool.
It is. It's very cool, and of course, if these 3 nodes come back online, as Jim mentioned, they'll just catch themselves up. The CockroachDB will self-heal itself, and everything will come back to normal. So this is just demonstrating that you can use the geopartitioned leaseholders and the duplicate index patterns. In a case like this, it gets you incredible resiliency, region level resiliency, and really good latency. But let's say that that's still not, that's not fast enough for you. Yeah.
Well, hold on.
Okay.
They say P99 latency, Jesse. That's P99. I mean,
yeah.
Are we getting even better than that in some situations?
Yes, you're absolutely right. Let me see. Okay, so it is P99, which means, outlier queries are influencing this metric quite a bit. So if we look at, I'm just going to pull up a custom debug chart. We have this pretty cool feature. And if we look at this, this is showing us 90th percentile. That means that 90% of all queries are at this latency or less. So in fact, 90% of queries are not 35 milliseconds. They're executing in, it looks like 10, 11, 12 milliseconds. So it's actually
even like
pretty
a third
fast.
of that.
Yeah, a third of that. Yeah.
So that's even faster than the P99. That's amazing.
Yeah, way faster. So,
but what if we wanted to get even faster now?
Exactly. If you want to get even faster, if you want like just immediate experiences, if you want users in New York to just have incredibly fast experience, as the same in Seattle, same in Chicago, we're going to jump over to yet another cluster and sort of demonstrate a different topology pattern. So it's the same exact setup here. But the key thing here to look at is the P99 latency is 3.1 milliseconds. So that means 99% of all queries are executing in 3 milliseconds. This is essentially the same as running in a single region. So we're looking at the single region cluster with just 3 nodes in a single region. Now we're looking at a 9-node cluster running across 3 regions, but you're still getting 3.1 milliseconds, which is just incredibly fast. And I want to again look at the databases page to show you what's happening here. Let's let it load up. The promo codes table, everything is working exactly the same. It's still a reference table. We're still using that duplicate indexes pattern to make sure that that reads are local. The cost-based optimizer always has an index that it can access. But let's look at, for example, the vehicles table. So the table definition is still the same, but I want to call out that the primary index has been partitioned. Actually, what did we look at before? We looked at users, I think. Yeah, I'm just going to keep it simple. So the users table, we still have those three partitions, just like we did in the last cluster, in the last pattern. The difference is only in the way the zone configs are defined. So here we have a zone config applied to the Chicago partition of the users table. And the constraint is a little different. The constraint says all of the replicas, basically all three of the replicas for a range of the Chicago partition, all of those replicas should be pinned to the US Central region. For New York, all of them should be pinned to US East. Seattle, all of them should be pinned to US West. And essentially what this means is not only reads are going to be local, but writes are going to be local too. So when you need to add a user to the users table in New York, it's never having to leave the US East region, which makes it incredibly fast. And let me see, I'm going to actually demo this once again in the terminal. All right, we're on the SQL shell here. All right, we're looking at the vehicles table, just like we did last time. And now these are the two ranges for the New York partition of the vehicles table. And you can see that all three of the replicas are pinned to the US East region. They're all on different nodes in the US East. Of course, the leaseholder is also in the US East. So Chicago, all three replicas are in US Central. Seattle, all three replicas are in US West. And the promo codes table is the same as it was before, so I don't really need to demonstrate that. But essentially, yeah, I mean, things are very, very fast because read and write operations never have to leave the region. So the trade-off that you make here is that you have AZ level resiliency instead of region-wide resiliency. So for, let's say, the New York partition, all of the replicas of that partition are in the US East region. So you can't lose the US East region. If you lose that region, you lose the New York partitions. The rest of the partitions are fine. The whole cluster is fine, but that partition is gone. So for a specific partition, you can only lose, one availability zone and still have a majority of the replicas. And so I'm gonna demonstrate that as well if I have the command. All right. All right, so I'm just going to take down, this is a different cluster, geo replicas. So I'm going to stop. Oh, I have to get off this VM. Sorry about that.
You're in Roach Prod.
I was using Roach Prod. I'm going to do this from my machine here.
And Roach Prod is just a tool we use on the back end internally to control something.
That's right. That's right. Okay, so what we've done right now is we've stopped one of the nodes in the US West region. And so we can see here, node 7. These are the 3 nodes in the US West. So Mover is operating for Seattle users out here. One of the 3 nodes went down. But we can see that Mover is still operating. It hasn't stopped. And even in the US West, it's still making progress. You're going to see in a little while, if we waited, you'd see the latency go down to 0 and the QPS would go down to 0. Let's actually filter by node 8. So this is one of the other nodes in the US West region. It's still receiving traffic. So Mover in the West Coast is still going strong. So again, geo-partitioned replicas means that you can survive an availability zone outage per partition. The promo codes table can still survive an entire region outage. So those are the 4 patterns that I wanted to demonstrate to you all, and just to review what we've seen. And we started with a single region cluster with the basic production pattern applied to it. So three nodes across 3 AZs, and we had local reads and writes, very, very fast, 2-3 milliseconds. Here's a screenshot, 2.8 milliseconds. And we could survive an AZ level outage because we still had a majority of everything. Then we went to a multi-region cluster. We didn't do anything at all. So reads were generally cross-region and writes were cross-region for sure. And in that case, latency P99 was 70 to 150 milliseconds, but we could survive the outage of an entire region. Then we went and said, okay, well, in a multi-region cluster, we really got to apply some topology patterns. So we applied the geopartition leaseholders and the duplicate indexes patterns. And so for the partitions, we got local reads because the leaseholders for those partition ranges were always in the relevant region. And we got local writes for the reference table because we created multiple indexes and made sure leaseholders were available in each region. But writes for all of it was cross-region because the replicas were spread across. And it went down from from 142 millisecond P99 to 35, which is a huge improvement. And we retained region level resiliency, which is awesome. But imagining that we just needed to get it quicker, it just needed to be snappier, we then went to another cluster. We applied the geopartition replicas pattern. That was the only change. Geopartition leaseholders to replicas. And the difference is we pinned all the replicas for a partition to the relevant region, and we ended up with local reads and writes for those for all the partition data. And again, local reads for the reference table with cross-region writes. And we're writing to that table so infrequently it doesn't matter. And we got back down to 3.1 milliseconds. So yeah, so those are just some demonstrations of topology patterns that you can use, especially important when you're running across multiple regions.
Jesse, thank you. That's phenomenal. I know it was a lot of work to get all that done and everything. There were a few questions during your talk that I didn't want to disrupt because honestly, you're doing a great job. So one of them actually came back. I was talking about this as the HA proxy was load balancing as well, but somebody had a very explicit question. So say I'm querying, say node 9, and node 9 goes down, will it redirect the query to another node?
Yes.
Yeah.
So the way that we've configured HA proxy in each region is HA proxy has a config that knows about the servers in the relevant region. And so it's gonna if it's trying to send requests to node 9 and it's not able to reach it, it's going to balance it over to node 7 or node 8. Yeah.
And that goes back to every node, or every node is a single consistent gateway to the rest of the database, and that there's no like write nodes and read nodes. There's no like, one node's doing one thing that's different than everybody.
That's right.
Everybody's the same, and it's just one binary, and they're all just participating together. It's true distributed system.
Yeah, absolutely. It's all symmetrical.
Yeah.
Yeah.
So the other question we had, and this is a little tricky too. So in the, in your last scenario, we had, 3.7 millisecond P99 latency where we had, data being tied to a 3.1. All right, fine. Yeah, pretty good. All data being tied to a particular region.
Yep.
When that region goes down, what happens to data that needs to be written to that, and how does Cockroach deal with that?
Sure. So that's the compromise you make. So when you do geopartition replicas and you basically constrain the replicas for, let's say, the New York region all to the US East region, when that region goes down, that partition is unavailable. So you have to, the other partitions in the West and the Central, they're still making progress. They're still fine. But on the US East, that means service interruption for your mover application. Typically you would use, process managers. You might use Kubernetes orchestration. You would want to monitor your cluster, and you see that it's going down. You restart it. Once you restart it, everything heals itself perfectly. So, yeah. But when you use geopartition replicas, you can't. Each replica can only tolerate an AZ level failure.
Yeah, and that's, it comes back to how we started the whole webinar. There's trade-offs. Yeah. There are trade-offs in topology, and that it's a great question because the person who's asking obviously understands the trade-off. But in the other instance, you could have 30 millisecond latency, which isn't bad, and still survive that regional failure, right?
Absolutely, absolutely. Yeah, it's all what's more important to you. AZ level failure, that's pretty good. I mean, to be able to tolerate, you know, and the other thing is, in this case, you know, when one AZ goes down, you're fine. When two AZs go down, then that's the equivalent of a region level failure. But the likelihood of two AZs going down at the same time is incredibly low. But you do have to think about what's most important to you. And if latency is of utmost importance, and you can live with AZ level resiliency per partition, geo-partition replicas is just amazing. To get 2 to 3 milliseconds in a globally distributed cluster is kind of crazy.
Yeah, and it really just comes down to the trade-offs. And I guess this is where we started, and we'll end here too. It's understanding both the physical and logical world here is, I think that's where this comes together, right?
Absolutely, absolutely.
And once you get your head around that, right, I think it's probably one of the most difficult spots, or one of the most difficult problems with CockroachDB. Would you agree? I mean,
yeah, I would agree. I think it's a SQL database, so that's not too complicated, but you do, like Jim said, you have to think about the physical reality. You have to think about where data actually lives. The thing is, Cockroach makes it incredibly trivially easy to do this, but you have to think about it. And one thing I want to mention is, like, those, the last two patterns, you know, you didn't have to do anything to the application. All you had to do was change zone configs. Right. That's it. We didn't have to change the schema, the table schema, nothing. We just had to change zone configs, and the cluster reacts. But you have to put some thought into it. And actually, I want to use that as an opportunity to call out the docs on this, if that's okay.
Yeah, God, please.
Because, you know, I sort of rushed through all that, but everything that I talked about is mapped out in our documentation pretty well. And these are somewhat new. So we have all of these patterns described here. But if you drill in to one of the patterns, you're going to see you know, some of the fundamental concepts you need to figure out, like what a basic cluster setup is going to look like. And then for each of these patterns, you're going to look at the steps that you need to do, the actual mechanics of implementing this topology pattern, as well as the characteristics you get for reads, the characteristics you get for writes. And I want to call out that specifically for geo-partition replicas, we have a pretty robust tutorial. And over the course of the next quarter or so, we're going to actually roll out a tutorial to map to every topology pattern. Yeah, so please go try this out.
Yeah, I will do another commercial for Joe. So Jesse leads our docs team and our overall education strategy here, and the team has done a phenomenal job in our documentation. And I don't just say that because I work here. I don't say that because I think Jesse's a good guy. I say that because as I onboarded myself into Cockroach Labs, I use the documentations heavily, and I've never seen a product so well documented. So kudos to you and your team, because honestly, it is phenomenal. Everything that Jesse just spoke about today is outlined in this topology patterns section of the documentation. So if you're downloading and using CockroachDB today, you want to start playing with, you know, geo-distributed and these nuances actually become extremely important. Like Jesse said, running Cockroach in a single region, we're going to be pretty good. And there's not a whole lot of, you don't have to start dealing with zone configurations, one zone basically, right? So, you know, you don't really have to do so much optimization, but you start getting into zone configurations across regions, understanding these things is just, it's really important. I think, Jesse, thank you. You've done a phenomenal job basically going through this with us today. So with that, we had a couple questions. I asked them towards the end there. But, you know, thank you, Jesse, and thanks everybody. Thanks, Maria, for helping out here. Thank you, everybody, for joining us. We will have another webinar on September 12th, how to get started with CockroachDB.